Let's talk about a way of creating new groups from old ones. This is called the product of groups. So given two groups G and H, you can put a group structure on the Cartesian product of the set G cross H. So I just need to tell you what is the group law on G cross H. So you can take G1 comma H1 and I need to tell you how to multiply it by G2 comma H2. And the answer is you just do it component wise, G1 G2 comma H1 H2. Okay, and you can easily check that this satisfies the group axioms. That is, this product will be associative, will have an identity, and every element would have an inverse. Now let's look at an example. So one example is, let's look at Z mod 2Z cross Z mod 2Z. So what is the size of this group? This is a group of order 4. And here's a question: is Z mod 2Z cross Z mod 2Z isomorphic to Z mod 4Z? That's another group of order 4, right? Well, the answer to this question, if you think about it a little bit, is obviously no. Why is that? Well, in this group Z mod 2Z cross Z mod 2Z, you take any element. Is of the form A comma B, where A, B are both in Z mod 2Z. And if I take this A comma B, this element A comma B, and now the group operation here in Z mod NZ and so on, I'm going to use addition. So I'm going to use the additive notation, and so if I take this element and add it to itself, I'll get A plus A, B plus B. But this is 2A comma 2B, which is 0 comma 0, the identity element of Z mod 2 cross Z mod 2. So when I defined the product of two groups, I didn't tell you what its identity element is. It turns out that the identity element of G cross H is the identity element of G cross the identity element of H. You can check that this works when you check that G cross H, as defined here, satisfies the axioms for a group. So what we have is that every element of Z mod 2 cross Z mod 2, when added to itself, gives 0. But in Z mod 4, there are these elements 1 and 3. That is, the residue class is 1 mod 4 and 3 mod 4. So 1 plus 1 is 2 mod 4, which is not the same as 0 mod 4. And 3 plus 3 is also 6, which is 2 mod 4, which is not 0 mod 4. So these two groups, Z mod 2 cross Z mod 2 and Z mod 4Z, cannot be isomorphic. Because if you had an isomorphism, where would it take the elements? you had an isomorphism from say Z mod 4 to Z mod 2 cross Z mod 2, where would it take the elements 1 and 3? There would be no place to take them because every element here has the property that if you add it to itself, you get 0. Okay, so, but let's look at another example. Z mod 2 cross Z mod 3Z. It turns out that this group is isomorphic to Z mod 6Z. This is a special case of a very ancient theorem going back to 3rd century China, the Chinese mathematician Lao Tzu, called the Chinese remainder theorem. So I'm going to explain this Chinese remainder theorem and its proof to you now, and uses a few simple ideas from group homomorphisms and a certain counting result. So recall that if you have a group homomorphism phi from G to H, then you can talk about the kernel of phi K in G such that phi of K is the identity of H, and you can also talk about the image of phi. This is the set of phi of G where G is G. And we've seen that this, I'm going to call this K here for brevity. We've seen that K is a normal subgroup of G. So K is a normal subgroup of G, and what's more, the left cosets or right cosets are the same since it's normal. Kg is equal to those, maybe I'll write Kg0 is those G in G such that phi of G is phi of G0. And so the cosets of K are indexed by, are determined by where they map under the homomorphism phi. So what we have is a bijection from image of phi to G mod K. This bijection, if you take an element in the image of phi, it's always of the form phi of G0. This corresponds to the coset G0 K. I'll let you check that this is a bijection between the image of phi and the set of cosets of K in G. Now what we know is that the cardinality of G is equal to the cardinality of K times the cardinality of G mod K. So this is just of course the cardinality of kernel phi, and we just saw that the cosets of K correspond to points in the image of phi. So this is the cardinality of image phi. So what we have is this. You can write it as a theorem for every homomorphism phi G to H of groups, the cardinality of G is equal to the cardinality of kernel phi times the cardinality of the image of phi. Okay, what does all this have to do with the Chinese remainder theorem? So I'm going to look at the following homomorphism. So you have two integers m, n, whose GCD is 1. So let's say these are positive integers, and the GCD of m and n is equal to 1. Now you have this group Z mod mnz. So if you were taking m to be 2 and n to be 3, this would be Z mod 6z, and you have a homomorphism to Z mod mz cross Z mod nz, and I'll let you check that this is a homomorphism. The residue class of x mod mn goes to just the residue class of x mod m and the residue class of x mod n. This is a group homomorphism. And the Chinese remainder theorem says phi is surjective. This is an onto map. Okay, Lao Tzu didn't state it this way. The way Lao Tzu stated is that suppose you have two numbers m and n which are co-prime, then you can specify what remainder you want modulo m and what remainder you want modulo n. Then you can find a number which satisfies both these, which gives both these remainders simultaneously. So for example, if you want a remainder of so let's take m equals 2 and n equals 3. So if you want remainder, if you want an element 1 comma 2 in z mod 2z comma z mod cross z mod 3z, so you want an integer whose remainder is 1 when divided by 2 and whose remainder is 2 when divided by 3 modulo 6. So then you can just take 5 modulo 6. 5 mod 2 is 1 mod is 1 and 5 mod 3 is 2. So that's the way Lao Tzu stated it, but it's just the same as saying that phi is surjective. And we can prove the Chinese remainder theorem easily, or rather deduce it from a very basic fact in number theory, that if m and n are co-prime, and x is an integer such that m divides x and n divides x, then m times n divides x. Okay, I'm not going to prove this. You can look up a proof if you're not already familiar with this. It's a basic result in divisibility of integers. Now, what is this really saying about phi? So what this is saying is that the kernel of phi, what is the kernel of phi? Kernel of phi is x belongs to z mod m and z such that x is congruent to 0 mod m and x is congruent to 0 mod n. Okay, so but that's the same as saying that you look at x belongs to z mod m and z such that m divides x and n divides x. But that's the same as saying that you're looking at x in z mod m and z such that mn divides x. But that's just the singleton 0. I mean the identity of z mod m and z. So kernel of phi has only one element, is singleton. So what we get is that, so we have this earlier result here, counting theorem, that the cardinality of G is the kernel of phi times the image of phi. So here what we have phi from z mod mz to z mod mz cross z mod nz. So what is the group G? The group G here is z mod mnz. So what we have is the cardinality of G, z mod mnz is the cardinality of the kernel of phi times the cardinality of the image of phi. But this has size 1, so this implies that the cardinality of the image of phi is, well, this is Mn, this is 1, so the cardinality of the image of phi is Mn, which is the total size of Z mod Mz cross Z mod Nz. So phi is surjective.